Here's another thermodynamics question which explores this idea of finding the minimum or the maximum of one of the properties of the gas during a certain process. And this is the kind of question that you might encounter as a first year engineering student if you're doing something like aerospace or mechanical engineering. And it might be something that you might see even as a high school student if you're preparing for something like a competition or an Olympiad. And if you'd like to see anything similar to this on the channel, let me know down in the comments. So let's read the question and let's see how we can approach it. It says, find the minimum attainable pressure of an ideal gas, I guess, in the process given by this. So the process tells us how the temperature depends on the volume. Okay, so let's write that here. Its temperature as a function of volume is some value T naught plus some constant alpha times V squared, where T naught and alpha are positive constants, so that's good to know. And V is the volume of 1 mole of gas. So if we start with the ideal gas law, which is this, we have the number of moles here. So technically the question tells us that in our case n is equal to 1, right? So we have PV is equal to RT, and that's the form of the ideal gas law that we can use here. And then it says draw the approximate P versus V plot for this process, and we can only draw an approximation because we don't know any values. Okay. Now what I'll do is I will actually start with the plot, and then I will go on and find what that minimum pressure actually is. Okay, and to do that, I will try to find a formula for pressure as a function of volume, because if the question is asking to plot P against volume, you need to know how the pressure depends on the volume. So we know how the temperature depends on volume. So let's try to see how the pressure does. So what I'll do is I'll take this temperature as a function of volume and I'll just sub that in the ideal gas law. So we have PV is equal to R times T. And instead of T, we have T naught plus alpha V squared. Okay, so we can take this and now we can just say that the pressure, so this pressure here, I'm making it the subject, so I'm dividing both sides by V, and we end up with this. And then if I put the V inside, that will give us T naught over V plus alpha times V, basically. Okay? Right, now before I try to find what that minimum value of P is, let's try to plot this. So on a PV diagram, we actually have two functions that we have to add up. So we have this one, we have T naught over V, or actually R T naught over V, because we have to multiply with R. So R T naught over V is a hyperbola, it's a rectangular hyperbola actually. So that's going to look something like, it's an approximation, but it's going to look something like this. I think you can make it a bit better. Okay, that's good enough. And then the other one, so the other function is R times alpha V. So the first one is RT naught being a constant, by the way, over V. And the other one is R alpha V, which is just the equation of a straight line. So the straight line looks like this. And if you add them up, you'll notice that the actual function, the actual pressure function with respect to volume is going to look like this. So it's going to start close to the yellow line, then it's going to reach a minimum, and then it's going to start approaching the green line. It's going to start going asymptotically towards the green line as V approaches infinity. So what will happen, and what we will show that is the case, the minimum, it's not too obvious in this drawing, but the minimum will occur when those two functions are actually equal to each other. So that corresponds to our, let's call it V star, and this is going to be our minimum pressure. And this is what the problem wants us to find mathematically. Okay, and it's quite easy to do that. All you have to do is just write P as a function of volume equals to R times, and then we have T naught over V plus alpha V, and then we just differentiate the pressure. Okay, we just do dP by dV is equal to 0, which means that this will give us minus RT0 over V squared plus alpha R. Okay, and that has to be equal to 0 to find the stationary points, and then we have to find what V squared is. So we can cancel out an R. R is just a constant, non-zero constant. So alpha is equal to T naught over V squared. So V squared, the volume, I should call it V star. Actually, so this V star squared is going to be T naught over alpha. So V star is going to be square root of T naught over alpha. So at this volume, we're going to get a stationary point. But now we have to show that this stationary point corresponds to a minimum. So let's differentiate this again. So we have d squared p over d v squared equals, and if we differentiate this again, we're gonna get, let's see, so this is gonna cancel out, and we're gonna get RT naught over V to the power 4 times 2V. So this is going to be 2RT naught over V cubed, which is positive. It's always positive because R is positive, so this is positive, this is positive, this is positive, and if the second derivative is always positive, it means the function is convex. So P is a convex function, and if it's a convex function, it can only have a minimum, right? So this corresponds to the minimum. So to find the minimum pressure, all we have to do is just plug in the value of V star in here and here, and that's going to give us P min. So P min is going to be R times, and we have T naught over, instead of V star, I have T naught over alpha under the square root, and then we have plus alpha times V star. So that's square root of T naught over alpha, which is R times, and then we can cancel out this like that. And we have R times, and then in the brackets we have square root of alpha T naught plus square root of alpha T naught, which is going to give us 2R square root of alpha T naught. Okay, and if you actually knew what alpha and T naught were, you can find the value of the pressure, and of course it's going to be newtons per meter squared in pascals. Okay, now another way to do this without using calculus is to use sort of like a mathematical trick, which is the following. So let's write the pressure value again. So you have pressure as a function of volume is R T naught over V plus alpha V. So let's look at this bracket here for a second. There is this kind of like a theorem, but it still stems from calculus in a way, which says that if you have two variable terms, which you do, so you have T naught over V, which is a variable, it depends on V, and you have this other term, which also depends on V. So if you have a sum of two terms, the minimum value of the sum happens if the two terms are equal to each other. So you have T naught over V equal to alpha times V, and indeed you'll see that if you rearrange for V squared, you're going to end up with V squared equal to T naught over alpha, or V is just square root of T naught over alpha, which is exactly the same thing as this, right? So whether you do it with calculus, whether you do it this way, if you want to avoid using calculus for some reason, you should end up with the same thing. And that's the value of the minimum pressure, and that's the end of the question.